In this video, we examine how the Gibbs energy of a reaction changes with the composition of the reaction. Alright, let's think about a very simple chemical reaction in the gas phase, which would be the synthesis of ammonia from nitrogen and hydrogen. Nitrogen reacts with 3 moles of hydrogen to generate 2 moles of ammonia. Right. Up to this point, we know how to calculate the reaction Gibbs energy under standard conditions. And then this simply can be done by obtaining the Gibbs energy of formation of products and then subtracting reagents multiplied by the stoichiometric coefficients. Now, if the sign of that delta G happens to be negative, then the reaction is spontaneous under those conditions. And if it happens to be positive, then the reaction will not be spontaneous under those conditions. Now, that is quite useful, but there is a huge limitation to that prediction. And the limitation is that everybody has to be at standard conditions. All right, remember that standard conditions are those where you have pure substances and also 1 atmosphere of pressure. Okay, so the prediction of spontaneity would imply that you have 1 atmosphere of pressure for ammonia, 1 atmosphere of pressure for hydrogen, and then 1 atmosphere of pressure for nitrogen. Right, so while that is useful, that's still very limiting because you can't predict spontaneity if the pressures are not 1 atmosphere for all of the substances. Right, so what we do in this video is try to come up with a way to predict spontaneity in a reaction at any conditions that you want, right? So suppose that you have no products, no ammonia, and then say 7 atmospheres of both reagents. Would the reaction be spontaneous under those conditions? Or suppose that you have 7 atmospheres of ammonia and then 1 and 1. Would the reaction be spontaneous then? Right? So we need a better predictor than this because this only provides the prediction for spontaneity if we are at standard conditions. Everybody needs to have 1 bar pressure or atmosphere. All right, so it turns out that we have worked out the way that the molar Gibbs energy depends on concentration for a gas. The way that it does so is as this. Okay, so the Gibbs energy of a gas at a particular pressure P is equal to the molar Gibbs energy of that gas at a pressure of 1 atmosphere or 1 bar plus a correction, which is RT natural log of the pressure that you're interested in, the actual pressure of the gas divided over the pressure of the reference state, which is 1 atmosphere or 1 bar. We're not going to see how this equation is derived, but this is something that we will do in physical chemistry in a few years. Now, from this definition, then we can actually go and try to see if then we can calculate what the Gibbs energy of a reaction is under any conditions and not only at standard state. Right, so notice that this gives you a measure for the Gibbs energy of any substance. Right, and now we can take that into the calculation of what the Gibbs energy of the reaction would be under any conditions not at the standard state, and that is simply going to be equal for this reaction as the Gibbs energy of product minus the Gibbs energy of reagents. So that would be 2 times the molar Gibbs energy of ammonia gas minus the Gibbs energy of reagents, which will be the molar Gibbs energy of nitrogen, which is a gas, plus 3 times the molar Gibbs energy of the other product, of the other reagent, which is hydrogen, a gas. All right, great. Because now we have the definition of these molar Gibbs energies as a function of pressures and some other factors, then we can develop this expression into something that is going to be more useful. Okay, so this delta RGM is going to be equal to 2 times the molar Gibbs energy of ammonia at the standard state. I'm not going to write the subscripts gas because all of them are gas and I want to save some time here, plus RT natural log of the pressure of ammonia over the pressure of the reference state, that is 1 atmosphere, and then minus reagents. So that will be the molar Gibbs energy of nitrogen at the standard state plus RT natural log of the pressure of nitrogen over the pressure of the standard state, and then plus 3 times the molar Gibbs energy of H2 at the standard state plus a correction from the fact that you're not at the standard state, partial pressure of H2 over 1 atmosphere. Alright, great. So what we're going to do then is actually collect all of the terms that are alike. Notice that those are all molar Gibbs energy at the standard state. Alright, so this reaction Gibbs energy under any conditions that we wish is going to be equal to 2 molar Gibbs energy of ammonia at the standard state minus the molar Gibbs energy of nitrogen at the standard state minus 3 times the molar Gibbs energy of hydrogen at standard state. And then we have the rest of the terms, right? So the rest of the terms are going to be RT natural log of the partial pressure of the gases divided over the reference pressure. Now, something that we have to be careful about is that we have to factor in this stoichiometric coefficient, right? So when you distribute that into here, you will have 2RT natural log of the ratio of the pressures. But you can take that factor 2 and put it inside of the logarithm as a power. Okay, so let's see how that works. Notice that that is going to be equal to RT natural log of the partial pressure of ammonia over the standard pressure, but now that is to the power of 2, because that is the stoichiometric coefficient, and that is how it enters the logarithm. And then you will have here minus RT natural log of partial pressure of N2 over the partial pressure at the reference state. Here you don't have any stoichiometric coefficient, so that's just the power of 1. And then finally for hydrogen, this will be RT natural log of the partial pressure of H2 cubed over the partial pressure at the reference state, which is 1 atmosphere cubed. Okay, so this is your new expression. Alright, great. Now we're going to be starting to consolidate terms. Notice that what you have right here is a term that is known. This is simply the balance of the molar Gibbs energies of products minus reagents multiplied by the stoichiometric coefficients at the standard state. This is exactly what we know how to calculate. That's just simply the molar Gibbs energy when everybody's at the standard state. And again, we've seen in a prior video how to calculate this with either molar Gibbs energies of formation or the molar enthalpies and the molar entropies of the reaction. Okay, so that's nice because we know how to calculate that quite easily. And then we have this term. Okay, so what we're going to do here is just take common factor of RT, and then we will have that this will be the sum or difference of natural logarithms, and then we're going to use the simple rules of logarithms to consolidate that quite well. All right, so there's going to be RT, and then you will have the natural log of the following term. Let me actually write this a little bit lower, plus RT natural log of the partial pressure of NH3 over the partial pressure of the reference state squared, and then divided, and that's because you have negative signs, right? That will be the partial pressure of N2 over the partial pressure at the reference state times the partial pressure of H3 over of H2 over the partial pressure of the reference state cubed. Okay? Alright, so let's write this once more. Delta RGM, the standard state plus. Notice that by convention, the standard state is defined as everybody has a pressure of 1 atmosphere. So that is 1 atmosphere, that is 1 atmosphere, that is 1 atmosphere. Notice that we can cancel all those out, but that means that these partial pressures that we would need left over would need to have units of atmospheres, and then the units of all this will be none. You won't have any units. Okay, so again, what these partial pressures do is simply cancel the unit that you have as long as those pressures are in atmospheres. Okay, so we can rewrite this simply as RT natural log of the partial pressure of NH3 squared over the partial pressure of N2 over the partial pressure of H2 cubed. Alright, so this, in my view, is the most important equation in all of thermodynamics because it allows you to predict the spontaneity of a chemical reaction under any conditions that you wish. Right? So now the only thing that you have to do is design what are the pressures of nitrogen, hydrogen, and ammonia that you have in your particular experimental setup, And then you will be able to predict under those conditions whether the reaction will be spontaneous or not. Notice that that is a significant step forward in our understanding of the spontaneity of the reaction, because until now we could only use this, which was simply the spontaneity when everybody was under standard conditions, 1 atmosphere of pressure. Now we can actually do this without having that restriction of the standard state. As a matter of fact, this equation can be generalized because you can recognize right away what this is. Notice that that is just the concentration or the partial pressure of products squared divided over the partial pressure of reagents to the power statistical error coefficients, and that is what we call the reaction quotient, as we have seen before, right? So your final expression is going to be delta Rg under any conditions that you want is going to be the molar Gibbs energy of the reaction at the standard state plus a correction, which is simply RT natural log of the reaction quotient. Okay, so again, I'm going to frame this equation because, in my view, is if not the most important equation in all of thermodynamics, is certainly one of the most powerful ones. All right, so again, it allows you to predict here whether a reaction will be spontaneous or not under any concentrations. If instead of gases, this would be solutes in an aqueous solution. You would have here concentrations as opposed to partial pressures. But again, you can do that under any set of conditions that you wish, and that carries a lot of power. In the next video, we're actually going to see what happens when we are at equilibrium. Okay, and then that will be able to connect the value of the Gibbs energy of reaction at the standard state with the equilibrium constant.